Okay, sorry. Okay, so yeah, so let me finish the statement about last time about the holomorphic lifting theorem. So uh, okay, yeah, sorry, not about holomorphic lifting, not about holomorphic lifting theorem, but it's about the holomorphic. Yeah, as well showing that a covering space is a automorphism. Yeah. Okay. Sorry. A transformation is automorphism. Yeah. Okay. So here the idea is that so here we have this x cuda as the holomorphic covering space of this x, and then wait, sorry, I think I should go the other way. Yeah. So here, okay. So here, okay. So here we have this as x cuda as the holomorphic covering space of x, and then this gamma is the holomorphic covering map. Sorry, holomorphic covering event surface of this x, and then here this is another holomorphic covering event surface, and then of this. Sorry, this is the same holomorphic covering event surface, and then we have this. So between the same space, we have this phi as the covering map. Sorry, as the Dirac transformation. Yeah, as the Dirac transformation. So such that so we have the phi composed with gamma is equal to gamma. Shoot, what I'm doing. So yeah, so it should really be yeah, sorry. Gamma composed with phi is equal to gamma. Okay, gamma composed with phi is equal to gamma. Okay, so right now what we have is, so okay, so basically we yeah, so you can check that the property of this x cuda and the map satisfy exactly the condition of the theorem that I stated last time. It's about the holomorphic lifting theorem. Yeah. So they satisfy exactly the condition of the holomorphic lifting theorem. So therefore, yeah. So this is the lifting of. Okay. So yeah. So since this phi is a lifting, or together with the phi inverse, okay, is a lifting. Yeah, for the phi inverse, you just yeah, you just do the phi inverse, okay. Okay, so then by theorem 5.1.3, which is the holomorphic lifting theorem, this is home. So we have yeah. So we have that this phi is holomorphic. Phi and phi inverse. And this is enough to show that this phi is an automorphism. Yeah. So it is a bijection, and then it is holomorphism, and then it has a holomorphic inverse. Okay, so therefore it shows that it's an automorphism. Okay, so okay, so right now what do we try to show? So yeah, so this implies that, okay, so this implies that it's so since this phi is in the Dirac transformation group, so this implies that this Dirac transformation group is actually a subgroup of the automorphism group. Okay. So use letter x tilde. Okay. All right. So let's try to prove the corollary 5.8, sorry, corollary 5.1.8, okay. Okay, so wait, shoot. Okay. Sorry. Actually, I misspelled. I look at the wrong theorem. Yeah. So it should be 5.1. Okay. So theorem 5.1.6. Okay. So proof of the theorem 5.1.6. Okay. So yeah, let me quickly state this. Yeah, state this here. So here we have okay. So here, what we have is that okay, maybe let's draw it here. So here we have this x tilde, and then we have so x tilde is the holomorphic universal universal covering space of the Riemann surface X. Okay. So this is a holomorphic universal cover. Okay. And then this okay, so then okay, so the conclusion is that okay, so actually there are two parts of the theorem. So one part is so one part is we have the gamma, which is equal to the Jack transformation group of this vertical gamma is a subgroup of the automorphism group of this S student. Sorry, that X properly is continuously and freely on X student. Is continuously and free on X student. Okay, so that's the first part, and then the second part says that there is a unique holomorphic structure on this the exterior closure knob by relation of its gamma, giving rise to a commutative graph diagram. Okay. Okay, so let me just show the first part, and then I'll state the second part, and then yeah. Okay, so let's see, how do we prove the first part? So, yeah, so for the first part, if this gamma is a subgroup of automorphism, yes, so we show that, okay, we just show that it's a subgroup of the automorphism, wait. Okay, so we need to show that it's a group, right? So basically, I think we show that this transformation is a group, right? Okay, so if you have two transformations, so if we have, yeah, I think they are also, because if you compose two transformations, so first it is a homomorphism, of course it's a homomorphism, and then if you if you do the composition, right? So if you have gamma, so that phi prime into like to Dirac transformation, and then you have this one as. So basically, what you do is that, yeah, I think this is equal to this one, and then this is equal to gamma. Yeah. Yeah, so it is indeed a group, right? Yeah, so that shows the other property of this. So, yeah, this the element definitely is contained in the Dirac transformation group, right? Yeah, because you compose with identity, then you get back to the same. Yeah, same gamma. Okay. So now, yeah, I think it's a group. Okay. So it's a group, subgroup of the automorphism of this x tilde, and then the x properly discontinuously and freely on this x tilde. Okay. I think this is from the theorem. Yeah. Okay, so let me check. So there's theorem 10.4.5. Let me check. So yeah, so theorem 10. Okay, so theorem 10.4.5 says that if this x tilde is the universal covering space of a connected, locally simply connected, locally comparable to X, then the gamma, which is being defined as the Dirac transformation group of this covering map, of this universal covering, and then X properly discontinuity and freely on this X tilde, and then the quotient map. Okay. Yeah. So basically, yeah, I didn't say the. Yeah, I just say here. Okay. So. Yeah, and then the quotient map is actually okay. Yeah. Okay. So here, right? So here, so the thing is that why this x is because we know that this x tilde is a universal covering, right? So that's for sure. So, but yeah, so this x is a Riemann surface, so therefore it's connected. So, but why is x? Oh, okay. So this because. Wait, do we have this x as locally simply connected? Let me see. Okay, so we need I need to verify that x is so what we need to here is that we need to show that this x is locally simply connected, right? Locally simply connected. Okay. I think this is true because this x is a Riemann surface. So for a Riemann surface, what you can do is that for any point, you can pick a chart that is homomorphic to this subset of Rn. And for subset of Rn, it is locally simply connected. So so that's locally simply connected. And then locally compact also. Okay, I think by the same, So using the same argument because it's a homomorphism. So yeah, you can show that it's locally compact also. Okay. Of course, for a manifold, it is so it is a Hausdorff space. I think for a manifold, you require the space to be a Hausdorff space, right? Sorry, I'm just trying to, So, hold on. Yes, you have to define it as a Hausdorff space be a manifold. So let's see for the Riemann surface. Okay, yeah. So this is all. Yeah. Okay. So yeah. So here we have all this. Okay. And then okay. So and then it's a locally compact household. Okay. Right. So we have that. Okay. So we have that. So yeah. So this part is being verified, and then let's see what happens next. So